good morning, and good afternoon, and good evening, everybody, wherever you are, and welcome to another session of Expand Your Horizon. I'm very glad to have with us Dr. Jennifer Holmgren. Hi, Jennifer. How are you today?
Wonderful. Good to be here with you.
Thank you very much. Which part of the world are you in today?
Colorado. My home
Colorado.
is in Colorado. Yeah.
Nice. Thank you very much for joining us, and a pleasure to connect. For those of us who don't know, your company LanzaTech has been interacting with Vestolit, one of our groups. So we have a relationship that spanned in the last couple of years, and we'll learn more about that. So thank you very much for all the support, and thank you much for taking an hour of your busy time and joining us today.
Thank you. Thank you for having me.
With pleasure. So, ladies and gentlemen, we will soon hear the very exciting story of Jennifer and the company that she is leading, LanzaTech. Truly inspiring technology and a global opportunity to make a huge impact. I want to remind everybody that we usually keep 10-15 minutes at the end for Q&As. So if you have any question throughout the presentation or towards the end, feel free to use the chat box, punch in your questions, and we'll curate all the questions and we'll present them to Jennifer at the end. And I think that's about it. Let's have fun and let's kick it off. I'll introduce you, Jennifer, just very, very shortly for the people to know, a couple of snippets from your background, and then you can take the lead on the presentation and share some of the more interesting stuff. So, as I said, Dr. Jennifer Holmgren is the CEO of LanzaTech. LanzaTech has developed alternative chemicals and fuels that are basically carbon neutral or almost carbon neutral, including the first alternative jet fuel, and we'll hear more about it. Jennifer has authored or co-authored around 50 patents and more than 30 scientific publications. So quite impressive, if I may. And she has a PhD in inorganic chemistry from the University of Illinois and an MBA from the University of Chicago. I hope we got all that pieces of information correct. And let's hand it over to you, Jennifer. Thank you very much, and the floor is yours.
Thank you so much. And I really appreciate the invitation. Every time I've interacted with the broader Orbia team, I'm so excited about your focus on sustainability and innovation. And so hopefully you'll see that topic resonates with you as much as it resonates with me. I'm gonna share my slides, if I may.
Please.
I grew up in Colombia. I was born in Barranquilla, Colombia. And like everybody in my generation, I followed the space program and I wanted to become an astronaut. What I learned later actually is that it wasn't my love for going to space, but rather my love for the fact that things that people said were impossible became possible in a very short period of time. And it was innovation and the technology that supported that inspired me. I came to really appreciating the impact of climate change a lot later. I had focused on energy democracy, and my interest was on making sure everybody on this planet had access to power. 1.3 billion people at the time that I was looking, and probably still today, did not. But what I learned in my reading is that if climate change was left unabated, by the year 2050, Colombia, my home country, would not be a coffee producer. That really made me appreciate that climate change was a fundamental change to our ecosystem, to our way of life, and that it would happen in our lifetime. This was just 10 years ago. And now, as you know, we can't turn around without realizing the fundamental change that we are making. And when I think about transitioning our economy away from fossils, I share a picture of my rescued greyhound. Everything in her life comes from fossil carbon, from the foam in her bed to her toys to her collar, even to the production of her food. Everything starts life as fossil carbon. And so this ambition that we have of bending this carbon curve, which seems unbendable, is actually a much broader ambition than we are prepared to admit. We talk about fuels and we talk about power being derived from fossil carbon, but 30% of today's fossil carbon actually ends up in all of the things we use, including everything that makes the life of my greyhound good. Everything starts life in a central location where petrol and other fossil resources are brought to a central location where they are converted to the things that we use in our daily lives. This is the economy that we must change. This is the economy that's fundamental to our lives. But today in 2022, this economy is absolutely not fit for purpose. It's very clear that while it has made our lives easier and better, it is certainly not the future. And I think the only way we transition away from this is if we're willing to admit to ourselves that all carbon is precious, not just carbon in diamonds, and we need to lock it all away and only take it out when we absolutely need it. I would argue that energy can be carbon-free. There's absolutely no reason today, with the levelized cost of electricity from fossil resources and renewable power basically being equivalent, for us to waste any of our carbon budget on power. But chemicals, and Shai and I were talking about chemicals as we were kicking this off, we have to have carbon. Chemicals are made with carbon backbones, and some fuels like aviation fuel are critically important, and we need the hydrocarbons and the energy density to literally right now get a plane from Orlando to Gatwick. And so we need to reserve our budget, our carbon budget, for fuels, heavy fuels that are required, and for chemicals. But I would argue that where the carbon comes from for those products is what will define our climate future. I would also argue that waste resources or carbon that is already above ground can be the essential feedstock to make all the things that we need, whether that be an industrial gas resource, whether it can be CO2 captured from the air, or a solid waste like biomass, like municipal solid waste. These are all carbon-rich resources. The carbon from the ground has already been used once, and we can use it again to make the products we need. And what I hope to show you during this presentation is that we're already doing that. You're seeing a Zara dress made from recycled emissions, a detergent, Unilever, EVA foam for shoes. All of these things we have already made, some of which are commercially sold from recycled carbon. So how do we do it? And the way we do it is we do gas fermentation. So you're used to the fermentation of sugar. You're used to making beer or wine by taking sugar and yeast and making beer. What we do is we make beer, but we start with gases: hydrogen, carbon monoxide, and carbon dioxide. We ferment them with a bacteria, a naturally occurring bacteria. We do it in a continuous bioreactor. So when you make beer or wine, you put it in a casket and you leave it alone for a long period of time. This is more like a refinery process, which happens in seconds. And so you're literally bubbling your gas in through the reactor. The bacteria sees it, eats it, converts it to ethanol. We recover the ethanol. So that is basically what we do. And where can you get these gases? industrial off-gases are often rich in carbon monoxide, hydrogen, and carbon dioxide. You can take solids and gasify them to make the same gases that I'm talking about. And if you want to use CO2, you just need to make sure you have hydrogen. And in that case, you would want to do some electrolysis or something like that. At the end of the day, all of these resources can be used to make ethanol, but ethanol to me is not a blending component for gasoline. Ethanol is a feedstock. Most of today's chemicals, one of the largest chemical feedstocks is ethylene. You can take ethanol, convert it to ethylene, and make everything else that today is made from ethylene. You can use the ethanol to aggregate the waste, carbon, and energy in all of these distributed resources. Ag residues, industrial off-gases, these are distributed resources. You're not going to build 200,000 barrel a day refineries using these waste resources. But once you make ethanol, ethanol is a liquid and can be moved, and then you can use that to make jet fuel, marine fuel, polyester, etc. And that is what we're doing. And of course, if you did you have a question, Shai?
Yeah. Just to play back what I heard and make sure I understand. So, to put it in my simple own words, you take carbon that already exists in certain places, whether in gas forms or solid forms, and the uniqueness of your technology is that you can take these different forms of carbon and then using gas fermentation to create ethanol, which is basically carbon-free ethanol because it came from sources that you did not generate any emissions in order to collect them, right? And
That's
then
right.
and that carbon or that ethanol can be converted either to fuels or to ethylene in producing all kind of other materials. And I think our people here at Orbia, at least many of them, are familiar with the process of converting ethanol to ethylene, and we know the ethylene polymer pretty well. A quick question. So I understand that when you create ethylene and then you produce a certain material, then this carbon is locked in that material until it is being recycled, and hopefully it is being recycled and not land dropped. But when you use it as a fuel in aviation or marine or trucks, I just look at the picture that we have. So when you burn it, it actually is being released to the atmosphere, right?
Yep. Yep, and you're absolutely right. And so I will show you then the next slide, the next click on this slide, because you got to the heart of the problem. You have to absolutely take any CO2 and recycle it back. And so CO2 conversion becomes extremely important, or direct air capture coupled with conversion, because otherwise, like you said, you're emitting the CO2 at the back end as you burn it. You still get the benefit that you've kept fresh carbon in the ground and you're reusing, so you don't get those emissions, but nonetheless, you're combusting and you're getting CO2. So as you rightly said, we got to recycle it. And then the other piece that you mentioned, we can no longer just dump all of our things in a landfill, right? We need to bring them back, put them back in the cycle, and convert them back into useful product. So actually, you are 100% correct that the future needs to be fully circular in this way. That's the only way we'll succeed.
Including the combustion gases from aviation and marine. And so your view of the future is even those applications that will still use a certain combustion process, the gases will be collected somehow.
Right. As long as you're going to do combustion processes, yes, they have to be collected. I would say, in my view, the aviation industry will actually change significantly. You're going to need combustion for the long-haul flights. I think electric aviation will become important for the short-haul flights. So I do think that electric EV approaches are emerging. There are a lot of people banking on hydrogen as the feedstock instead of hydrocarbon, and then you'll get rid of the CO2. I think in the next 20 to 30 years, it'll be more of a combination of hydrocarbon, which requires CO2 capture, and electric aviation.
Thank you.
Thank you. Thanks for that question. What I just showed you is not science fiction. This is actually our first commercial plant. We started it in 2018. It's operating in China. It's produced more than 50 million gallons of ethanol already. And what it does is the steel mill gas is rich in carbon monoxide, between 45 and 55%. Instead of letting it go out the flue, what would happen is it would be flared, converted to CO2. We actually just put a compressor into that and we pipe it into these bioreactors. And in these bioreactors, we convert the CO2, this carbon monoxide, before it's converted to CO2, into ethanol. And so we now have 3 of these plants running in China, 1 at a steel mill, 2 at ferroalloy mills. And I think this is exciting to show that the technology works at scale. I'm a chemist, as Shai mentioned, not a biologist, but I do believe that biology is an important path for the future. Biology is more robust in terms of dealing with contaminants. And if you really are using waste, you don't want to be cleaning waste, right? Once you've cleaned it, it's probably not waste anymore. And so something that can self-replicate and evolve in a way that if there are contaminants, it can handle it. Something that can build a simple molecule across many scales to larger molecules is important, and something that is extremely selective. I talked about centralized refineries where you convert 200, 300,000 barrels a day. Waste is distributed, and so you need to have something that's extremely selective, because if it is selective, then it allows you to only have one unit operation next to the waste, rather than like in a refinery where you do a conversion, it's not completely selective, then you have to convert that product in another operation and then another and another and another. So this selectivity is something that biology can do. But the other thing biology can do, just like us, is it can handle and interpolate chaos. When we see this, we know where our cars should go because we're making decisions in chaos. Biology is like that, right? And with waste is not homogeneous. So what you're looking at here is the hydrogen carbon ratio of municipal solid waste in one of the plants we built in Japan at a pilot scale with our partner Sekisui. Plastic hydrogen carbon ratio is very different than woody waste hydrogen carbon ratio. And so you can see these fluctuations as this mass of trash literally goes through the gasifier and is converted to syngas. On the other side, you see all the attributes I told you. The biological organism is interpolating across these hydrogen carbon ratios. The organism can make its own hydrogen from carbon monoxide to adjust for this variability, and therefore what you see is a very flat line in terms of selectivity. It doesn't care what you feed it. It needs to survive and will be successful at creating the products it needs. The only thing that happens is at the lower carbon ratios, you get less yield because I can't magically appear carbon. So, but if you think about it, this is the power of biology and why a distributed approach will be quite useful. This is actually our commercially operating plant in China.
Sorry, Jennifer, maybe just another question. You used the term syngas, and I'm not sure all the people really understand what it is. So maybe like 2 sentences on that.
Yeah. Thank you for that. Actually, syngas is an abbreviation for synthesis gas. Chemists believe that if you give us carbon monoxide and hydrogen, we can build anything. And so we call the mixture of carbon monoxide and hydrogen syngas, for short for synthesis gas. Thank you for asking that, Shai.
And in this specific example, you're talking about municipal waste that has been collected, burned in some sort of a process, and the gas that came out of that process is actually a synthetic gas, basically a combination of carbon monoxide and hydrogen.
That's right. And it is burned, but it is not a full combustion. In a full combustion, you would just see CO2 and water. This is a partial combustion, and it's done with something called a gasifier. People call partial combustion systems gasifiers. Take solids to gas, and that's how you get carbon monoxide and hydrogen.
Yeah, thank you.
Thank you. So our first commercially operating plant that I showed you, reactors, this gas is actually carbon monoxide only. It's not a full synthesis gas. There is no hydrogen. Our organism has to make the hydrogen, and it can do that. There is chemistry called water gas shift, where carbon monoxide and water can be converted to hydrogen and CO2. So if the organism doesn't have hydrogen, it will make it. What you're seeing here is the carbon monoxide in the gas. It's literally fluctuating between 45 and 55% on a second-by-second basis. The organism is still able to make ethanol. At the lower levels of carbon monoxide, of course, it makes less ethanol, but nonetheless, it is making ethanol. This ability to handle waste streams like this is tremendous, and it's important, I believe, in really being able to leverage a waste future.
And Jennifer,
Yes.
can you say a word about these organisms? Are we talking about certain organic creatures that do all of that?
It's a bacteria.
Okay.
It's a Clostridium. It's just a type of bacteria, and it's an organism that's naturally occurring, and through directed evolution we optimized it. So we didn't genetically modify it. It produces ethanol naturally. We just optimized it so that it would only make ethanol, and it would make it efficiently.
So this bacteria basically likes to, if I put it again in very simple words, it likes to eat or consume syngas, so carbon monoxide and hydrogen, and then it produces in that process ethanol.
Correct. Absolutely correct.
And those bacteria are easily scaled. Like if you need to do hundreds of those plants or thousands of those plants, there's abundance of those bacteria.
Yeah. So actually, what we do is we got the original organism from a library. There's a library in Germany, basically, that collects all organisms. And so the founder of the company, Sean Simpson, brought the gas-eating organisms to New Zealand and tested them to see which ones were the best. What we do once we have the organisms we want is we actually produce large quantities and freeze dry them. Okay, so we make them in the US and then we freeze dry it like you do yeast, and we ship it to China, where we start up the reactors with these freeze dried bacteria. So actually they grow in the bioreactor. We actually just send a tube, and that tube eventually becomes what is swimming in these bioreactors. And we grow them up stepwise, and within a week to 10 days we have a full capacity operating plant. So that's how we do it. So you don't need to make that much because they are self-replicating. They're alive. And I should tell you, because everybody gets nervous when I say they're alive, they don't like oxygen. The only thing that will really kill them is oxygen. So it's an anaerobe, an obligate anaerobe, which means in the presence of oxygen, it will literally die. So it doesn't take much oxygen to kill it. If it ever got out of the bioreactor, it would be quite dead. We do remove it from the reactor because it is dividing in the reactor, and we don't want to plug the reactor. As I mentioned, it's a continuous bioreactor. We dry that and we sell it as animal food. It's 90% protein. So that's our only co-product is animal food. We like to say you have to cross the valley of death to get to your first commercial plant. This is typical of process technology. Our company's been around for 17 years. The first commercial plant started up after 14 years. You literally need to go one step at a time to larger and larger scales. We did not skip steps. We built multiple pilots, multiple demos across the world, making sure we were using real gases that were contaminated. We wanted to make sure our organism was not a lab prima donna that literally would die in the presence of a real gas. And we built our first commercials. They get very expensive. These plants are $50 to $200 million, the commercial plants. And now we're in the process of literally diffusing the technology across the world to ensure that we as a company become a viable enterprise. Like Orbia, we want to be able to make more money than we burn. And so that's where we are right now in our stage of development. This is an older slide. We have 2 operating plants, actually 3 as of a month ago. 6 more under construction and 7 more in engineering. We license our technology, so it's our partner capital that is being used to build the plants. We receive a small percentage of the revenues, but the key is that what we're trying to do is build these plants across the world so that everybody can have the opportunity to see this type of biology at work, and also so we can show the various gases from municipal solid waste to steel to refinery to CO2. We're trying to show that the technology is broadly applicable. So we're really excited about this progress. So, as I said, ethanol is just a building block as far as I'm concerned. It's just a feedstock by which we can make everything else. You can take ethanol to ethylene and make paraffins, isoparaffins, which is what aviation fuel is. You can also convert it through ethylene to all of the derivatives of ethylene. We have successfully done that and introduced products in the market based on our ethanol. So our ethanol is being used in Coty perfumes, in detergents that are being sold in Switzerland at the Migros stores. Zara has introduced 2 collections. Lululemon has made some fiber. We've made PET bottles from it for use in smoothies. Sometimes recycled PET doesn't have the quality to allow you to put it in food or pharma grade, but this is virgin. This is like virgin PET because we recycle at the fundamental carbon level. And so those materials can be used for food and pharma. And then in addition, because they are like virgin materials, they get put right back into the cycle because they can be mechanically recycled. Aviation fuel, we've flown planes from Orlando to Gatwick, from Boeing Field to Tokyo. We are now building a larger plant. We're working with On Shoes on making the EVA with Borealis for their shoes, and glycols for Unilever. Just a couple of quick examples. I already mentioned cleaning, ethanol cleaner being sold in stores already. Coty perfumes, this is the production plant. This is only on a pilot scale. This is commercial and this is commercial, but we have worked with Total and L'Oreal to make polyethylene for packaging. I already mentioned we've made PET for bottles. What's really quite interesting is we recently announced working with Danone, and I'll talk a little bit about this later, such that we use synthetic biology so that we don't have to go through ethanol. to take all of these wastes directly to different chemicals, and I'll talk a little bit more about that. And that's kind of the holy grail, because you bypass all of these steps and you go directly to the product you want. These are 2 dresses that were introduced by Zara. That's a material that Lululemon made for running shorts. You can see the white. Normally recycled PET doesn't give you that type of very white material. I told you on shoes, we're working with Borealis to make EVA. And of course, in the pathway to MEG, monoethyl glycol is a key raw material for polyester and PET chips for bottles. You go through ethylene oxide, and with ethylene oxide, you can make surfactants, and those surfactants can be used in detergents. And those are 3 detergents that Unilever has introduced that use surfactant made from steel mill emissions. I want to stop you for a second, because I've gone through this very quickly, and I would like for your mind to at least be blown a little bit by the fact that the carbon in the products I've shown you here actually was a steel mill gas, right? That was a byproduct of making steel, and that was going to end up going out of flue as particulate emissions and CO2. And it really is important for us to appreciate that carbon can come from things that are already seen at first use, and that really something unimaginable, that a steel mill gas could end up in your clothing, has happened. And it's not science fiction. It's happening. This is something that I, at least if anything, as a takeaway, I would like that to be your takeaway.
And Jennifer, maybe on that, are there, there are other, let's say, emission-heavy industries other than steel mills? I think you mentioned a couple of others, but what about cement, power plants, aluminum plants? All these are like on the top list of, do we have a similar process for these guys?
Yeah, so right now we've been focused on steel, ferroalloy, and refinery. We are looking at cement, and we are looking at aluminum. Some of them do have the gases. Of course, they all have CO2. And so we could always use the CO2, but some of them also have carbon monoxide, which is an easier food. When I use CO2, I have to have hydrogen. Now, you asked me about power. Yes, this can go on the back end of a power plant, but if it's end-of-life power plant, you need to remember that for us to convert CO2, we need hydrogen. And we need hydrogen that's stoichiometric to convert all of that carbon into products. That's a lot of power to make green hydrogen. And so if you're at an end-of-life power plant, you're probably just better off. You need so much power to convert to CO2, you're just better off going with renewables. If you're at the beginning, then yes, you can imagine adding hydrogen to be able to convert it. So we are looking at those options.
Okay, and two other things that are very relevant to Orbia. We operate jointly a large ethane cracker to produce ethylene. Are the emissions of that process are suitable for you?
Absolutely, and I can imagine, for example, integrating into a plant like that, using the emissions and then adding an E2E plant in front, ethanol to ethylene plant in front of the cracker. And so then not only do you use the emissions to make CO2 to make ethanol, but then you convert that ethanol to ethylene, and then you can leverage the cracker separation to separate the ethylene from other products, right? So you could build an ethanol to ethylene plant and mass balance into your cracker rather than, dedicated ethanol to ethylene line to make products, right? Initially, you could just combine our ethylene with your ethylene to get some mass balance benefits.
Yeah, and ethanol to ethylene is a pretty known technology, right?
It is, and that's what Indian Glycols has an ethanol to ethylene plant in front of their MEG production plant. There are very few ethanol to ethylene plants running today. and we're working to try to get more recommissioned and started up. When the price of ethylene got low, everybody stopped caring about ethanol to ethylene, and then also everybody got a little nervous about first generation ethanol as a feedstock, making ethylene from corn or sugarcane. And so we need to now get that industry back up. And that was something I was working with your team, actually, to see if we could find somebody that was prepared to create the ethylene so that you could make PVC from that.
Yeah. And last question on that, another thing that is relevant to Orbia, we produce a lot of polyethylene products, so pipes and conduits. I mean, billions of meters. What's the message that we can give to these guys as they currently buy predominantly virgin and sometimes recycled polyethylene?
Yeah, so actually it's something we're really focused on, working with partners to add an ethanol to ethylene plant in front of a polyethylene production facility so that we could make some mass balance polyethylene. So I think that's something that will be available in the next 2 years with what we do. There is a company called Braskem that already makes polyethylene from ethanol. They use sugarcane ethanol, so that is already available on the market. And like I said, we're trying to get ethanol to ethylene plants in front of polyethylene, PVC, EVA production so that we can start making those products on a large scale from our recycled carbon ethanol.
Thank you.
Okay, so now, oops. Sorry about that. So we make ethanol using our microbe. That is a first generation microbe. It is not genetically modified. And what you can do is imagine genetically modifying a microbe to make other products. We already know how to make acetone. We already know how to make isopropanol. We're learning how to make MEG and other products with our microbe from gases. So you can imagine the plant that you've built being almost like the hardware, and then each microbe like software, because you can use the same plant, the same bioreactor, the same cleanup system, the same feed gas, not just to make ethanol, but to make all the other products, because this microbe has to live in a very specific environment. So once you build that environment, it doesn't matter whether it's the ethanol producing microbe or the isopropanol producing microbe. You can literally shut down this plant and 10 days later be making a new product if you had those microbes ready. And so this is actually something I see as the future, where these ethanol producing plants actually become chemical producers. You would have to change the separation. You don't separate acetone from water the same way you do ethanol from water. But nonetheless, what you're imagining is a future where your hardware is almost a toll manufacturing facility. And when the price of a chemical is high, then you would go ahead and make the chemical of choice. You can imagine 3-month campaigns, 6-month campaigns, making whatever chemical you need at your site at the time. It's a very different future. We have worked on this. Our acetone and isopropanol microbes have been piloted. You're capturing the carbon, as you said, Shai, at the beginning, when you were asking me about making products. And of course, this is very exciting because you bypass other thermocatalytic steps. And like I said, selectivity is quite important. So we think it's really important to imagine a world where we take those same products, like acrylics, like polypropylene, put them back in the cycle through gasification. Please understand that I am not saying this is better than mechanical recycling. This is complementary to mechanical recycling. There are places where mechanical recycling is actually a better solution. It's lower energy and it can serve the purpose. The point is to use mechanical and chemical recycling approaches like the one we're using to actually create, a future where we can eliminate fossil carbon from the supply chain by continually reusing. Our work with Migros and Mibel to make bottles, which are made from recycled carbon and then can be recycled into recycled PET. We did receive an award for that. But for me, what's important is by combining different approaches, we imagine a future where virgin fossil carbon can be eliminated from our supply chains. I want to talk a little bit about aviation fuel. This is a thermocatalytic process that we developed with Pacific Northwest National Lab. It is thermocatalytic, so it's very different than LanzaTech gas fermentation. So we spun it out into a company called LanzaJet. Suncor, Shell, Mitsui, and British Airways invested. ANA is a key partner, and the Department of Energy is also a key partner. We're building a 10 million gallon a year facility right now, and it should be up and running next year, and that will be a significant step. It can be any ethanol, any waste ethanol. It doesn't have to be LanzaTech ethanol, which is the other reason we spun it out. We wanted it to be able to access other ethanol if there was other sustainable ethanol available. This aviation fuel has some excellent attributes. It's a hydrocarbon. It does not have aromatics. It reduces particulate emissions. It has increased energy density. It has no sulfur. So it has real benefits, including lower contrails relative to conventional petroleum jet fuel. Okay, I'm going to go back to the beginning. Why are we doing all of this? We're doing all of this because of this. We can no longer afford to talk about 1.5 degrees, 2 degrees, 3 degrees. I mean, those are just different levels of climate tragedy. I believe that new technologies can rapidly transform how we view the world and how we make everything in this world. Solar is a perfect example of that. Solar didn't just bring power to places that didn't have power. It enabled a whole new economy, like this young man powering devices. These are devices that you couldn't have had in these villages. And you say, well, why do you need a mobile phone? Well, you need a mobile phone to know what fruit to bring to the market, to get paid, etc. So it is an enabling technology beyond just bringing power. I think it's also important to think that our mobile world, our distributed solar world, our distributed wind world is very different than the world we're used to, where we build centralized power plants, centralized refineries. And we believe that we can get economies of scale by building a lot of the same type of facility, not just building really big ones. And because waste is distributed, we believe this is an important enabler for waste. So I would ask you to look at the words of Buckminster Fuller. We will not change our fossil economy simply by trying to do exactly the same thing with different feedstock. We will change it by reconsidering the model by which we change things, by which we make things, and we change that. So when somebody asks me, well, can you build a waste to ethanol plant 200,000 barrels a day? That is not the point. I cannot compete with that because my waste resources are distributed. Petroleum is the densest liquid on earth. It lends itself really well to centralized locations. I have shared with you a vision of biology and a vision of what we are doing. Please understand that our company and our technology is not going to solve the problem we're in. And that I encourage you to consider all of the different approaches that can help us bend the carbon curve. It is absolutely time to rethink carbon. Our planet's on fire. We have to rethink refining. I want you to think that refining is about the conversion of CO2. I want to refine CO2, carbon monoxide, and hydrogen, not petroleum. I believe biology will have an important role to play and will enable us to make everything we need. I hope I've shown you that, so that every waste resource, including CO2, can be the things we use in our daily lives. From this to this, not science fiction, we're doing it already.
Carbon is all around us. We need carbon in our lives, yet it's too small to see. We figured out how to capture and reuse carbon instead of it going into our atmosphere. To do this, we use synthetic biology, AI, and engineering. How we source carbon will determine our climate future. We are on the cusp of a new industrial era. Instead of digging up carbon from the ground, we transform carbon from agricultural, industrial, and municipal wastes. We've completely rethought the process of manufacturing. Our future is one where our planes are powered by fuels made from atmospheric CO2, where emissions are transformed into fibers, furniture, and fragrances, where our shampoo bottles and detergent are made from pollution. LanzaTech's first commercial ethanol plant prevents over 75,000 metric tons of CO2 from being emitted annually. We're growing quickly, helping industries reduce their carbon footprint and bringing carbon-smart chemicals, materials, and fuels into our global supply chains. We've launched a sustainable aviation fuel company called LanzaJet. We have over 1,000 patents globally, and we are working with Fortune 500 companies to produce everyday products that are a part of a $1 trillion market. Our technology has proven what is possible. If this company sounds like a breakthrough innovator, that's because it truly is. Join the new carbon revolution. LanzaTech.com.
You can share that vision with us. And I thank you for taking the time to listen to our story.
Jennifer, thank you so much. Really inspiring. Couple of questions that come in from the audience, and we'll combine a few together. The first one is around the costs and the economics of those solutions, especially how they compare to current alternatives that are emission heavy. What's the current cost and what's the future outlook looks like?
Yeah, so for example, our PET, our MEG our PET is more expensive, 2x-ish, even from recycled PET, so it is more expensive. But a lot of the costs are in shipping the ethanol, because we don't happen to have the production of ethanol in a location where we can also take that ethanol to MEG. So we doubled the price easily by just transporting ethanol around. So our way to drive down the costs will be to create integrated solutions where we can go all the way from the waste to the ethanol. And it doesn't have to be integrated at one site, but at least we don't have to move it from China to India, where Indian glycols is, right? So we want to build plants in India where we can just truck the ethanol to the location. So a lot of our cost is in that, but yes, it is more expensive, but we are driving it, not by driving necessarily the cost of the ethanol down. We're doing that too, but also by trying to not have to spend, significant amounts of money in transportation.
If you compare the cost of I don't know, 1 ton or 1 kg of ethylene in a most optimistic scenario in the next, I don't know, 2, 3, 4 years, do you see it coming down to a you know, kind of like a virgin or today type of ethylene cost?
No, I mean, ethylene is in the 400 to 500 range in the US right now. I think adding another process step, the ethanol to ethylene, will make it very difficult to achieve those numbers. But I can see getting so that you're 1.5x rather than 2 to 3x. I think that's sensible, even on an ethylene basis.
Yeah, and then if you think that hopefully at some point there will be some carbon taxes added to the, you know, the traditional processes, it might help get the cost parity.
I think that's right. If you ever get to a carbon tax, I think that's what I heard you say. You cut out for a second. If you start to add a carbon benefit or a carbon tax, yeah, then it should be no problem getting to parity. Already in the aviation sector, we see that with the incentives, you get to parity.
Okay. The second question is around the process and how clean the gas, I mean the source gas, need to be in terms of free of all kind of like pollutants and particulates. Is there a limitation there?
So that's a great question. So particulates you always have to remove because compressors don't like particulates. So if you have particulates, you really do have to take them out of the system. Contaminants, it depends on what it is. Sulfur, nitrogen, the organism doesn't care. Cyanide, it does care, so we have to clean it. When you consider thermocatalytic processes, where you have to clean things to the ppb level, and here a ppm level is sufficient. So that's one difference. The other thing you'll find is if you kill, you know, a 200,000 barrel a day catalyst bed, right? You're gonna have to replace all that catalyst or regenerate all of it. In this case, actually, you just load it up. I told you the microbes go around freeze-dried, and it literally takes you 7 days with a canister of freeze-dried to get it back up. Sometimes you don't need to restart it even. Sometimes the culture will recover. It just depends on how much contaminant. So don't think of the contaminant levels here as being similar to thermocatalysts, but yes, there are definitely contaminants we have to remove.
And some specific material that you can't or can use. So for example, if you would, could you process chlorine in a recycled PVC? Is that an issue, or salt that exists in food, for example?
Yeah, there's no problem gasifying any type of food. So the MSW plant in Japan we've used is actually from a working commercial municipal solid waste site where they had an operating gasifier. So everything that goes in there, from woody waste to grass clippings to household waste, no problem whatsoever. Anything that's inorganic falls to the bottom. So if you have metals or anything else, just falls to the bottom. Only the organic portion is gasified and feeds our system. PVC with high chloride is something we need to look at, because chloride will kill the organism, and so a gas that's rich in chloride will be a problem. But we have gasified with partners, tires, carpets, shoes. So single as well as municipal solid waste. So I suspect it's possible to solve that problem.
Okay, maybe looking at the clock, and maybe last question before we conclude. What keeps you awake at night?
Well, the only reason I'm still working and not retired is climate crisis keeps me awake at night. And I think the tremendous urgency that we need to solve this problem, and the realization that technologies, even though I talk about technologies as being important, takes so long to scale. So how do we behave more urgently and compress the timeline to get new ideas across, where they can have an impact? Those are the things that I worry a lot about.
And do you see, or do you have an optimistic point of view? Do you see clues and signs that things are moving in the right direction? Because one could get a little bit pessimistic looking at the speed that things have changed in the last 5 to 10 years.
Yeah, well, first of all, I'm naturally optimistic. You can't do the types of things I do unless I'm optimistic. But, if we commit ourselves to solving this, we will solve it. The real question is, between now and then, how much suffering, I think is the only way to say it, will we have to endure? But I think I am seeing signs there's more commitment from governments. The fact that I'm even talking to you says your company is committed. It's just about going faster. And I am extremely optimistic. I see good signs, good directions. But more importantly, I see a generation of people that understands there's a problem. Got to recognize there's a problem before you can solve it.
Yeah. And maybe that's the perfect note to end our conversation. In a world full of bad news, this past hour was, at least for me, an optimistic perspective that things can look differently. So thank you very much for sharing that with us. Good luck with LanzaTech, and obviously we will do everything possible to help the revolution. And thank you for taking time and talking to us despite trying to save the world. We highly appreciate that, and thank you.
Thanks for having me. It was a real pleasure, Shai.
Take care, Jennifer, and thank you everybody for staying.